define probability measures, and we thought about some of the basic properties of probability measures. So let's do some examples of probability measures. For example, let's begin with our naive, what do we call, probability measure. Define a map from a, so obviously you have a sample space and maybe a sigma-algebra which you can treat as power set of omega, okay? And then I'm defining a map P from f to 0 to 1 by we can, maybe the better is to say that this guy is a finite set actually. So say it contains endpoints. It's a finite set. And the probability measure that you are defining, so on a event actually, which is obviously a subset from F, okay, is a number which contains, which is a ratio or a comparison of the points which are in A with the points which are in the whole sample space actually. Okay? And then we can see that it's a measure. Why it's a measure?
Sir, two axioms.
Two axioms must be satisfied. Obviously, if you take the probability of omega, you're going to get 1. Okay? And if you have...
Sir, it's
for
between
example,
0 and 1.
Huh?
It's between 0 and 1.
It is indeed between 0 and 1. Why? Because you have order of omega divided by the order of omega, so you're going to get 1 actually. And the next is that if you have a disjoint sequence of events and then you take their union, okay, with their union I equal to, for example, 1 to infinity, okay, AI, then this would be the order of union of I equal to 1 to AI and everything divided by omega. Okay, but infinity. But this infinity is not going to be infinity because this set is a finite set, obviously, so it's going to have some finite subset, so it's a finite union actually. So it's not something which is crazy. And since all these are disjoint, then we know the result that, okay, if you sum up, so if you take the disjoint union of, sets and see their order, so their order is going to be the sum
of orders of
1 to infinity, order of AI and everything divided by omega, and this simply completes the proof. Because it's a probability measure. But as we said, that this is not a good measure. Why it's not a good measure? Because it's a naive one, and why it's a naive one? Because that it just gives equal weights blindly to all potential outcomes, which is not a good way to do it. So a better way to define, for example, if you have the same thing, so same space, okay, so it's like omega is omega 1 to omega, and f is what you call the power set of omega, it will be a subcollection of power sets of omega. Better is to take it as power set of omega. Then you define, for example, these guys as, so for example, you take that, I'm defining probabilities, but on individual elements of it actually, so on singletons, okay? And I'm assigning them a number px. So to each omega I am assigning a number px, okay? And then sum of these pi's, I'm making sure that they give you 1. Okay? So such that sum of pi is 1. Now that's a better one. We can prove actually that if you, and obviously, okay, you need to define it on abstract A, which is A is an element of
P of A.
sigma
P of
field,
sigma.
okay, then you're going to say that, okay, those elements, you know, so you treat that as the sum of probabilities of those omega i's, okay, which belongs to A and take their sum simply, okay. Then this is also a probability measure.
So second example is satisfying this.
Okay. So here you are not assigning, you know, each of the outcomes of omegas as a what we call as, you know, an equal weight, but we are assigning them a weight accordingly. Okay. Something that you can define, you know, with your choice and with your relation, with the data that you have, and so on and so forth. Okay. So, you know, pretty.
What about second exam, sir? In this case,
Think about it. Show it for yourself that it's a probability measure. Okay? Because think about it. If you have disjoint union, okay, is going to contain disjoint omegas, and hence you need to add a disjoint PIs actually, the probabilities of disjoint omegas, so it's going to give you some PIs actually. And hence you can think cleverly and try to prove that, okay, whether it's a probability measure or not. Okay? So this one is a good measure. If your set is finite set, you know, while this is not, you know, it's not a good definition, but it's a measure. It's a way to assign chances. Obviously the natural question would ask that how about, you know, if this omega is not a finite set actually, okay, then what to do? Then you have different choices, you have lots of choices, you can do define them, you know, probabilities in different ways. Okay, before getting to that, I would like to define something called the Dirac measure. Okay, or sometimes it's called the unit mass measure. So what do? You take a fixed omega from omega, okay, and this omega is inducing a measure basically, okay. So sigma is a sample space. Take F to be, you know, the power set of omega, or maybe the better notion is that I'll use this symbol, okay, so power set of omega rather than increasing E with a P actually, okay. So if you take a fixed omega from omega and take F as the power set of omega, then I can define a measure delta, okay, corresponding to this omega, okay. So it's going to be a map from F into 0 to 1 such that if omega, so delta of omega when operated on the some event A is going to give you 1 if your fixed element is in that set A, and it's gonna that I'm not inside if this fixed element is not in A, or it's in omega minus A actually, so it's in complement. You have to be careful, this is not an indicator function, because the indicator function tells you what? It tells you that, so for the indicator function, okay, you can see that somehow as an indicator function of a singleton set, okay, but don't confuse it with an indicator function, okay, it's not explicitly as an indicator function. So you're taking a fixed omega, you're defining a map, and then you're saying that that map operated onto an event is going to give you 1 if the omega is in A, is going to give you 0 if omega is in
Is not
B.
in.
So then why we have considered closed set from 0 to 1? Why we have considered discrete points 0 and 1 only?
Where?
S omega is from F to the closed set 0 to 1.
No, that's my definition. I can define the way I want actually. So this delta is basically telling me the mass of this element actually. Okay, omega. That how much of mass is concentrated at this omega. So essentially what I'm saying that we have a map A. Okay. Okay, so you are saying that, alright, that why you are not getting a closed interval.
Why we are not getting just two discrete points 0 and 1?
So he's saying it's just abuse of interval. Like we have one interval, but we're taking just 2 points.
No,
0
come
and 1.
on, we need to grow up now. So this is your fancy codomain,
Okay.
while the range is 0 and 1. So, what I need to just show is that there is a way to, assign a number between 0 and 1, okay, to each of the elements in F actually. So I can write a discrete set 0, 1, which would be still fine, but I want to be consistent with the notion or, the abstract definition of probability measure that we take as that it's something from, the sigma field into the interval 0, 1 actually. Okay? Why this would be 1? Why this would be 1?
Because omega is in sample.
Because that's what you are starting from.
Yes.
Okay? That's what you are starting from. How about, think for yourself. Think for yourself about this joint unionness thing. It must be easy. It's not that difficult. Think about it. So what could be the potential relationship between this omega and this countable union?
Sum of.
So I have an element omega, and I have a disjoint union of the countable union of disjoint events actually, are the elements of F.
So there is AI is such that W comes.
If omega is in any of the AI.
Just one.
One AI.
Yeah.
So there would be, here's the thing, there would be two possibilities actually. We are missing one thing. Is it necessary that omega should be in the union?
So union is.
It's not necessary. So the first case would be that if omega is not in this union, okay, then the delta omega of this union is 0.
Okay.
Okay? But if omega is not in the union, then omega is not in each of these AIs actually. And hence, some will also be 0 actually. Anyway, think for yourself. It's not that difficult. Okay?
So, second condition.
Few things should be mystery, huh? To resolve by yourself. Is it making sense?
So this one is not a whole space.
Space नहीं होगा.
No. That's another kind of a confusion. This, we have, just go back and see the definition. Are we assuming that the union of the disjoint union is equal to the whole omega? So you will not find this in definition. So I can take a countable union of things and I can't still achieve the whole of omega. So, assuming that as this is equal to the whole of omega, it's not necessary actually. Okay. So it's redundant. We haven't assumed it. Is it making sense? So think about it, that why it's a probability measure. So obviously you need to think the two cases, when omega is inside of it, when omega is outside of it. So this is what that you have to think of. And then this is called the Dirac measure, and or maybe the unit mass measure.
So is it related with Dirac delta function?
In some sense, yes, and in some, in reality, no, actually. So we can't give a. So you're using the same symbol delta, but there is a connection. Okay, there is a connection, but not explicitly. Okay. The Dirac delta function is a distribution, actually. Think about it. So it's not even a function. So it's a distribution. What do you mean by it? So it's a linear bounded functional. Okay. So it's a map from some suitable continuous space into the R. Okay. Anyway, so it's different from Dirac delta function. Okay. But you can see some similarities as well. Anyway. Okay. The next is, you have lots of examples here. Next is, you just see some examples from the book actually. There are two examples given. One is the binomial, so in the terms of the Dirac delta measure, there is something it's called the binomial probability measure, and there is something which is defined as, I think, probability measure defined through geometric distribution. Okay? Just go through them for yourself and try to prove that those are measures. Okay? So do hands-on practice, spend time on proving different kind of things as probability measure. I can see that the conditional probability, for example, instead of taking omega, I'm taking, say, so imagine I have omega fp, here's another example, interesting one, is a probability measure already, so it's some probability measure, and you take a fixed b from f, okay, alright, I'll show that this fixed b and the probability measure, this probability space is gives rise to, or it induces a new probability space actually. And that probability space is going to be that, okay, you define omega b, so this b is fixed. So it's a collection of, so it's a collection of intersections of A with this fixed B, where A are the elements from what do you call sigma field affected. Okay, so it's kind of an induced probability. I'm doing something stupid. So omega B is B. Just take simply omega B as B and define FB not as Facebook, but A intersection B, and A is from sigma field affected. What we can show, maybe the first question would be to think that is this a sigma field? Okay. And then define a probability measure B from this FB into the 0, 1. Okay. The interval 0, 1 as that if you operate probability B onto some x actually, okay, it's going to give me the probability. So this probability measure, okay, times x, okay, into, okay, let me define this notion, okay. So probability of A given B. I haven't defined this actually, what is the meaning of this, but I know that I can define this as probability of B x given B, x intersection B by probability of B. Okay. So what does this shows is that if you have a probability space, then you can have a new, so for each fixed B, you can have a new probability space omega, so omega b, fb, and the probability measure induced by b, and this probability measure is going to be the conditional probability. So in other words, conditional probability, so if you define a measure in the terms of a conditional probability, okay, then the conditional probability is also a measure basically. Okay? It's a measure. So verified, there will be lots of examples and exercises waiting for you, okay, on LMS. Okay, so do all these, make sure that you understand things, and then we can move on.
So we have to prove this is a probability measure.
So you have to prove that this whole is a probability space actually.
B is a
So first you have to show this is a sigma field, then you have to show it's a probability measure. Good.
Sir, this drag measure, is this just the only definition of drag here, or we can also define another definition?
I can, so that's the basic way to define it. Okay, that's the basic way to define it. I haven't seen anything, or maybe there is another way to define it, but I haven't seen anything except this. Okay, is this making sense?
Yes, sir.
So, lots of work for you. So, in the next thing that I would like to move on. The next thing that I would like to move on, basically I want to do two things today. And I want to do something serious in next course, next session, so that you can do all these funny things for yourself. Alright. So spend time on doing exercises. It's going to give you a good sketch of what you are doing. So what is the philosophy? The philosophy is that instead of assigning the equal chances to all possibilities, okay, the better is that you define the measuring of chances in your own way actually, okay, the way you want. So this is the notion of probability measures are more flexible, more powerful, and it generalizes the all previous ideas actually. Okay? And you can already see that you can define continuous things. So it's like it simply generalizes discrete versus continuous, what do you call, probabilities and stuff like that. Next I would like to do what? Next I would like to get to a bit more abstract things. It's very much analog. It's not that different from what we are doing now. So as I said that I want this course to go into parallel ways. So we want to cover some measure theory, okay, and then we want to do the probability theory as an example of measure theory. Okay. So now I would like to move what? I would like to move to some of more, what do you call, abstract thing. Let's call the measure theory. Okay. But it's going to be pretty much simple. So previously we defined what's omega fp, so it's like what's a probability space. So now I'm going to define that what's a measure space actually. Okay. And obviously we have already done one example of measure space, that is probability space. Probability space is an example of measure space. Okay. So let's begin with the algebra. Okay. So whenever you hear this word algebra, so one of the things we have to be careful. Okay. This algebra has many different meanings. Okay. So it's like you go in linear algebra. The algebra has a very different meaning. That it's a kind of a vector space in which you can also do the multiplication of things actually. So in vector spaces, we've just defined scalar multiplication and addition. That how you can multiply a scalar with a vector actually. But in algebra, you say that okay, let's take two vectors and multiply them actually. Okay, so that's a different algebra. Okay,
It's a set.
so it's a completely different thing. So here you have algebra from analysis point of view. So you'll see that there are many terms which are shared, which are used same as, for example, in algebra and analysis, but they have completely different meaning. Okay, maybe there is some connection, but there's a very different meaning actually for all those. So you don't confuse those with. So when someone asks algebra, so it's like you have to ask what algebra. Algebra from measure theoretic point of view, algebra from algebraic point of view, what algebra, and then answer appropriately. Okay. So what's in algebra? So let's take a set X. So X is an arbitrary set. Obviously, we are interested in non-empty sets. Okay. So what's in algebra? So if X is a set, then I have a collection of subsets of X actually. So it's a calligraphic A. So I'm going to denote this by calligraphic A. And A is what? It's a collection of subsets of X actually. And this calligraphic A is algebra. If what happens, pretty much the same thing that you learned in the case of the sigma field. Number one, that empty set should be there. Okay, empty set and X both should be in algebra. And the second thing is that it's closed under intersections. In other words, if A is in calligraphic A, then a complement must also be in calligraphic A. Okay, and the third thing is that if you take a finite collection, okay, countably finite collection from calligraphic A, okay, then it implies that their union, okay, and the intersection also belongs to the calligraphic A. So if you have such kind of a thing, you call it an algebra. Right? Then we have something called sigma-algebra. Essentially,
So then this ordered pair will be algebra.
this ordered pair will be called an algebra. Okay, algebra on X. Okay, so this finite thing is important actually. Sigma algebra is essentially same as sigma field, so there is no difference between both. Okay, it's precisely the same actually. The only context is different. So whenever I'm going to use the word sigma algebra, you have to assume I'm in measure theory. Okay, so I'm asking from I'm talking from the perspective of measure theory. But whenever I'll use the word sigma field, which is quite often I'm going to use, then you have to assume that I'm in probabilistic sense actually. So the probabilists, they don't want to call sigma algebra as algebra, so they have created their own notations called sigma field actually. But it's precisely same, so there is no difference between both actually. The only difference is that obviously in sigma field, the X is going to be the probability, some sample space of some random experiment, and A is going to be the collection of the events actually. But essentially, it makes no difference. Okay, it makes no difference. Is it making sense? So what would be sigma algebra? So it's pretty generalization actually. We can also say that this is a more generalized version. So X is sigma algebra. Okay. If 1 and 2 is satisfied, which is from here, and the third property is different from here. And that is going to be that if you take the countable collection of, obviously, do we have a disjointness here? We don't have.